Okay, so in this lecture, we will discuss about magnitude, argument, and polar representation of complex number. Polar representation, right? So in real number system, we can define distance. Hence, we can define the magnitude of real number. That is how much distance away it is from the number zero. Like the number for the number say minus 10.5. How much distance away it is from zero? How do we define it? We defined using this magnitude mod of 10.5, which gives me 10.5, right? So then we need to define, we have a complex number system. So in complex number system, we also need to define a magnitude for any complex number, right? And for any complex number, say x plus iy, we define the magnitude is r equal to root under x square plus y square. Remember, we defined this complex number x plus I. We said before that the real number order pair x comma y, this can be we can represent it as complex number x plus iy using three operations, like using two operations, one addition and multiplication we have defined earlier. So here this magnitude we define here is the replication of the distance from 0 0 comma xy. Distance is 0 0 to x comma y. The distance is root under x minus 0 whole square plus y minus 0 whole square, which gives ultimately x square plus y square. So from here the distance or magnitude of a complex number comes, right? Now to represent a complex number, to put a complex number in the grid of a complex plane, we this distance only cannot help, right? We need also direction to put that complex number in the complex plane. So a measurement of the angle theta, that the point z, our point z equal to x plus iy, say, right? This is a complex point. So a measurement of the angle theta, a measurement of the angle theta, that the point z equal to x plus iy with the positive real axis is called an argument, and denoted by argument of z, which is basically theta, right? This is theta. So let's make it more clear that what is theta and what is r in the diagram. So this is my complex plane, right? This is real axis, this is real axis and imaginary axis, and this is the point z equal to x plus iy, right? The distance r is basically from 0 0, this point, this is 0, say, capital 0. We are defining this one 0. So 0 to this distance is the r, and what is theta, or the argument is this one theta. This the angle the point z makes with the positive real axis. This one is the positive real axis, right? Theta equal to argument of z. So now we can, now this theta and r, both of them can represent a complex number. If we write that, if we write some r and theta, both of them obviously a real number, right? R is the magnitude, which is a real number, and theta is the angle, which is also a real number. So both of this real number, we can, if we write it, then we can get an complex number z, right? This r and theta denotes a complex number z. From there we can derive our polar representation of the complex number. So so we may express the point z equal to x plus iy, or we can say this xy order pair in the form where the x equal to r cos theta, r is the magnitude and uh, theta is our argument, and y equal to r sin theta. So ultimately what we get, z equal to r cos theta plus r sin theta, which is we can write r of cos theta plus I sin theta. This is the polar representation of z. Polar representation of z, complex number, where r is the let me write it over here. R is the magnitude and theta is the argument. So uh, now uh, we can be wondering, like, why do we write x equal to r sin theta and y equal x equal to r cos theta and y equal to r sin theta? From where did we get? Let me just make it clear over here. We knew that this magnitude r equal to root under like when z equal to, when z equal to x plus iy, we knew that the magnitude r was r equal to root under x square plus y square. So from there we can clearly write x square plus y square equal to r square. So if we set x equal to r cos theta and y equal to r sin theta, in that case what will be getting, like if we set x equal to r cos theta, y equal to r sin theta, well, what will be getting in from this left hand side will give us r square cos square theta plus r square sin square theta, which will be r square of sin square theta plus cos square theta, right? Or cos square theta plus sin square theta, which is ultimately r square into 1, which is equal to r square, which gives you the right hand side. So from there we derive these notions: r equal to r cos theta, x equal to r cos theta, y equal to r sin theta. Okay, now we see, interestingly this r comma theta, which belongs to r, it uniquely determines a complex number. Like if we write r equal to say 5 and theta equal to maybe pi by 3, it will give me a unique complex number. What it will be? It will be 5 of cos pi by 3 plus I sin pi by 3, which is a unique complex number in this grid somewhere over there, right? Pi by 3, if we try to find what will be, like suppose this distance is 5, this is the circle of radius 5, and angle is the argument is pi by 3. So pi by 3 could be over here, right? This angle could be pi by 3. So our, and this radius is 5, this radius is 5, so our point will be this one. This is the z, this is our z point. That's how we determine. So this r comma theta can uniquely be determined a complex number, but if we write z equal to some alpha plus I beta, will it give me a unique r comma theta? Of course not. It will give me a unique r, but it will not give me a unique theta, but not unique theta. Why? Let's come to this point. See, when if we set theta dashed equal to theta plus theta plus 2k pi, where k equal to 0 comma plus minus 1 comma plus minus 2 comma dot dot dot, it will go like this. So for all of this k, we see that cos theta dash, this is equal to cos of theta plus 2k pi. And what do we know? That 2k pi plus theta, it will, cos of this will obviously give me cos theta, right? Sin theta dash, similarly sine of theta plus 2k pi, this will give me sin theta. So for all of this theta dash, for all of the values of k, will give the same cos theta and sin theta. Like what I'm trying to say, that for all the values of theta dashed, r comma theta dashed, will get the same value. Same, we will get z equal to r cos theta plus I sin theta. For all the values of theta dash will get this only one number. So we can easily see that theta is not unique, right, in this case. So that's why for this disbalance we need to define principal argument. Principal argument, which can be which we denote by ERG, capital ERG of Z. So what it is? This is the unique representative for this principal argument. Like for this for the values of this argument of Z, it will lie from minus pi to pi, right? From minus pi, over here this is the minus pi to, then this angle is pi. Like from the positive real axis, if we go in this direction, it will give, this angle is minus pi, and from if we go this direction, it will be plus pi, right? Plus pi and minus pi. So this argument of Z, this principal argument will give me my unique representation. See, so quickly let's just go some for example to compute this capital principal argument of Z. Like, right, if we said compute capital argument of Z for Z equal to say minus 1 plus I root 3, and Z equal to minus I5. So for Z equal to minus 1 plus I root 3, here x equal to minus 1 and y equal to root 3, right? And what did we know? X equal to r cos theta, y equal to r sin theta, right? So here we get r sin theta by r cos theta, this is equal to root 3 by minus 1, which is equal to minus root 3. So we get tan theta, this is equal to minus root 3. So basically this is minus root 3, nothing but the tan of pi minus pi by 3, right? So we get that theta equal to 2 pi by 3. So we see that here theta equal to 2 pi by 3, this is the principal argument, right? Over there theta is this could be some angle, and this is the 2 pi by 3.